Alright, in this video we study how we can use differentiation to find local maximum or minimum values. Okay, let's start. Suppose we have a continuous function on a closed interval between a and b, and we are interested in finding the maximum and minimum value of this function. Okay, so if the function looks like this, let's see, like this, for example, and this is A and this is B. Okay, and the minimum value of this function may be somewhere. So this value maybe. Oops. So this is the minimum value, and this value is obtained at this point x, and the maximum value is this one. Okay, so these are global minimum and global maximum values. Okay, it's global in the sense that this, okay, let's pick this global maximum point. This is the maximum value over the entire domain of this function. Okay, in this sense, it's global. Okay, and in general, finding global maximum or global minimum or global extrema values is quite hard if the function is complicated and the domain is large. So if we're lucky, we can find them, but if you're not lucky, maybe it's really difficult to find, even if it's possible. On the other hand, if we are not so interested in global extremal values, then we may find some local extremal values. For example, in this case, let's see, this point is a local maximum point. So if we just look around this region, then this is the point where the function takes the maximum value, around this point. Okay, so if we don't look entire domain, but only locally around this domain, this is the maximum values. It's called a local maximum value. And of course, any global maximum value is a local maximum value too. So this point is also a local maximum value. And this point it was the global minimum point, but it is also a local minimum point too. So instead of finding global maximum or global minimum, we may find local minimum or local maximum points. And finding local extreme values, or that means local maximum or local minimum, can be done by using differentiation or derivatives. Of course, we're assuming that the function is differentiable. But first, let's define what local maximum or local minimum values mean exactly. So here's the definition. Suppose we have a function f of x defined on an interval I, and also the point A is included in this interval. Okay, we say f of A is a local maximum value. Maximum value. So if we say this, what this means is this. Here's the definition. That is, there exists some positive real number delta such that if x is included in the open interval between a minus delta and a plus delta, actually we take the intersection of this interval with the domain of this function I. If x is included in this set, then f of x is, wait a minute, x is not equal to a, okay? then f of x is strictly less than f of a. If this holds, then we say f of a is a local maximum value. So what does this mean? This means, so if a function looks like this, around, let's say this is a, and this is a minus delta, and suppose this is a plus delta. Okay, x is somewhere in this open interval, then everywhere in this interval, the value of f of x is less than the value of f of a, as long as x is not equal to a. Okay, so that means if we consider only this open interval, f of a is the maximum value of the function. So what this means is that f of a is a local maximum value. So local means we are only considering this local region of the entire domain of the function. And when f of a is a local maximum value, then we say x equal to a is a local maximum point. Maximum point. Okay, there's a difference between local maximum value and a local maximum point. And we can define a local minimum value and local minimum point in a similar manner. So we say f of a is a local minimum point, a minimum value, local minimum value. And of course, a is a local minimum point. And this means, by definition, here's the definition, there exists some positive delta such that if x is in this open interval between a minus delta and a plus delta and intersect with I, and if x is not exactly equal to a, then this implies f of x is greater than f of a. Okay, so this means if we take delta, small enough delta, then we can make this inequality hold for all x in this interval, as long as x is not equal to a. So what this means is this situation. Okay, so maybe the function may continue something like this, and there may be some other point where the value of the function is lower than f of a. So let's say this is f of a. But we don't consider this case. Okay, we take delta that it's small enough. Okay, let's pick this delta. So a minus delta and a plus delta. So if we just limit our focus, attention to this open interval, that is a small interval, then the value of f of x is always greater than f of a. Okay, if this is possible, then we say f of a is a local minimum and x equal to a is a local minimum point. Let's consider a somewhat an extreme case where the function f of x is a constant. Okay, constant. So what is, let's say this is defined on entire real number. So what is the maximum or minimum value of this function? This is a constant function, so it's always same value. So the c is always the maximum value and the minimum value. But this value is neither local maximum nor local minimum, because this doesn't fit the definition of local extreme values like this, right? We never have this inequality, or or this inequality because it's constant. Now consider another example. F of x is equal to x squared minus 1 times x squared minus 4. So this function takes a local maximum value. Local maximum value at x equal to 0, and the value of f of 0 is 4. Okay? So if you just plot the graph of this function, it's obvious. So the graph should look like this. So if you factorize this function, then this is x minus 1, x plus 1, so this becomes this, and x minus 2 and x plus 2. So this function takes the value of 0 where x is equal to plus minus 1 or plus minus 2. So the function looks like this. And it's also even function, right? F of negative x is just equal to f of x because we only have x squared here and here. So it looks like this, something like this, and negative 2 and negative 1. This is not, scaling is not so good, but anyway, you get the idea. And at x equal to 0, here's the local maximum point. So if we limit our attention to, say, somewhere, let's see, so somewhere between this open interval, then this point is the maximum point of this function. So let's see if this is indeed the local maximum at this point according to the definition of a local maximum. So to do that, maybe it's useful if we rearrange this function a little bit. So if we expand this, we have x to the power of 4 minus 5x squared plus 4. So this plus 4 is the local maximum value when x is equal to 0. So let's factorize this as this and minus 5 and plus 4. Okay, so x squared is always positive or 0. And this one becomes negative. Okay, we want to show that this is strictly less than f of 0, which is 4, right? So this is negative if x squared is less than 5. So x squared is less than 5 means x is between negative square root of 5 and square root of 5. So now let delta be square root of 5 then. So if this is the case, then if x is in this open interval between 0 minus delta and 0 plus delta, which is between plus minus square root of 5, then if this is the case, and if x is not equal to 0, then x squared minus 5 is less than 0, and x squared times this is also negative. Therefore, f of x, which is this plus 4, is less than 4. So if we just add 4 to both sides of this and plus 4, we have this. So our delta is this, then this inequality f of x is less than f of 0 holds. Therefore, this is indeed a local maximum value, and x equal to 0 is the corresponding local maximum point. Okay, next let's see how we can relate local maximum or local minimum to differentiation. And for that, let us define a new notion of critical point or stationary point. That is, uh, let's say f is a differentiable function. Differentiable function. Okay. And we say x is equal to a is a stationary point or critical point. If f prime of a, so the differential coefficient at x equal to a is equal to 0. Okay, if that's the case, then f of a is called a stationary value or critical value. Stationary or critical value of the function. So this concept becomes important when it comes to evaluating local maximum or local minimum, because we have the following theorem. That is, suppose f of x is a differentiable function. Again, differentiable. Therefore, it is continuous. Differentiable function. And if f of a is a local extremum value, that means local maximum or local minimum, then f prime of a is equal to 0. So it is a critical point or stationary point. But we should be careful that the converse of this theorem doesn't always hold. Okay, that means even if we have the differential coefficient of 0 at x equal to a, it does not necessarily mean that f of a is a local maximum or local minimum value. Sometimes it can be neither. Okay, so let's prove this theorem, and we prove this only for local maximum case. Okay, for the case where f of a is a local minimum, it's similar. Okay, so suppose f of a is a local maximum value. Maximum value. And of course, if x equal to a is a local maximum point. So according to the definition of a local maximum value, then there exists some delta that is positive, such that if x is in between a minus delta and a plus delta, then f of x is less than or equal to f of a. Okay, in this case, we include the case where x is exactly equal to a. So this equality here holds only when x is equal to a. Okay, otherwise it's strictly less than. So we have this inequality to begin with. Now let's consider the differential coefficient at x equal to a. So f prime of a is, according to the definition, x going to a and f of x minus f of a divided by x minus a. Okay, so consider two cases. First case, if x is greater than a, then x minus a is, of course, positive. So in that case, maybe we should put equal sign here. F prime of a is, so this numerator, we have f of x minus f of a, which is negative or 0. So the numerator is non-negative, non-positive, and the denominator is non-negative. So therefore, the differential coefficient in this case is less than or equal to 0. It's non-positive. And second, if x is less than or equal to a, then x minus a is non-positive. And therefore, f prime of a is, so the denominator is non-positive and the numerator is non-positive. That means that, negative divided by negative is positive. So this is greater than or equal to 0. So this holds and this holds. And we're assuming that it's differentiable. So this should be equal to this, of course. So the right limit and the left limit should match. Therefore, if these two holds, then the only possibility is that f prime of a equal to 0. And we are done. An example. Let's go back to the previous example where f of x was x squared minus 1 times x squared minus 4. That was x to the power of 4 minus 5x squared plus 4. And we knew that this takes a local maximum value at x equal to 0. So let's evaluate the differential coefficient at x equal to 0. First, let's differentiate this once. So we get 4x cubed minus 10x, and that's it. And this is evaluated at x equal to 0, which is a local maximum point. This is equal to 0, obviously. So this is 0, this is 0, so this is 0. So indeed, the theorem holds. However, as we have noted before, the converse of this theorem doesn't hold. A good counterexample is this one. F of x is equal to x cubed. So if you differentiate this, we get 3x squared. And at x equal to 0, this differential coefficient is 0, right? But this function doesn't take either local maximum or local minimum at x equal to 0. If you plot this function, it looks like this. So it's a monotone increasing function. So here, it's not local maximum or local minimum, but still, it is a stationary point. Okay? So the converse of the theorem doesn't hold. Okay, that's all for this video. See you later.